Exact equations. An exact differential equation is one in the form of m of xy dx plus n of xy dy equals 0. To solve an exact differential equation, a knowledge of partial differential and multiple integration are necessary. Fortunately, these topics, while normally covered in Calculus 3, are easy to pick up on, so you need not take Calculus 3 to learn this topic. Partial differentiation. Suppose we wish to differentiate the partial of g with respect to x. There are two notations for this. We hold y constant as if it were a number, then differentiate the x's. In this case, the partial of g with to x is 8x times y cubed. Suppose we wish to differentiate the partial of g equals 4x squared y cubed with respect to y. There are two notations for this. The partial of g with the respect to y. What is the derivative with respect to y? The partial of g with respect to y is 12x squared y squared. Differentiate f of xy equals 2 times x to the 4th power times e raised to the power of 3xy. The partial of f with respect to x is 8x cubed times e raised to the power 3xy plus 6x to the 4th power times y times e raised to the power of 3xy and is obtained by the product rule. The partial of f with respect to y is 6x to the 5th power times e raised to the power of 3xy. And now let's move on to multiple integration. Multiple integration works in a similar fashion. You hold y constant and integrate with respect to x, or you hold x constant and integrate with respect to y. Integrate the integral of 4x times y cubed dx. This is the integral with respect to x. We should get 2 times x squared y cubed plus c, where c is an arbitrary constant of the integration. Now let's integrate with respect to y. The integral of 4x times y cubed dy. This is the integral with respect to y. You should get x, y to the 4th power plus c, where c is an arbitrary constant of integration. We now illustrate a method for solving an exact equation. Recall that an exact differential equation in the following form: m of xy dx plus n of xy dy equals 0. Theorem: if the following mn, the partial of m with respect to y and the partial of n with respect to x, is continuous to the region about x and y, then m of xy dx plus n of xy dy equals 0 is exact if and only if the partial of m with respect to y equals the partial of n with respect to x. Now for examples. Example 1. Is 4x squared plus x times y dx plus 3 times x plus y dy equals 0 exact? Remember to hit pause and calculate. M is 4 times x squared plus x times y, and the partial of m with respect to y is just x. N is 3 times x plus y, while the partial of n with respect to x is 3, and as these two partials are not equal, the equation is not exact. We would need to try another technique, and it might not be an easily solved equation. Example 2. Now let's solve the equation 3 times x times y dx plus, parentheses, 1 plus 3 over 2x squared, end parentheses, dy equals 0. Notice that both the partial of m with respect to y and the partial of n with respect to x are equal to 3x, so the equation is exact. phi of xy is the solution of the exact equation. Integrating with respect to x gives phi of xy equals integral of 3 times x times y dx equals 3 over 2 times x squared times y plus h of y, where h of y is some function of y to be determined. Integrating with respect to y gives phi of xy equals integral of 1 plus 3 times x squared dy equals y plus 3 over 2 times x squared times y plus g of x, where g of x is some function of x to be determined. Comparing the two versions of phi of xy, we get that h of y equals y and g of x is a constant. So the solution of phi of xy is 3 over 2 times x squared times y plus an arbitrary constant c.